We just got some great news. The National Science Foundation just gave us a boatload of cash to find some planets. So settle in while I tell you how we are going to put your tax dollars to work. This story starts around 2015 when my group, in collaboration with Olivier Guillon's group at Subaru Observatory, just managed to cobble together enough money to build a first of its kind camera to find exoplanets. Unlike the cameras you are used to that use semiconducting detectors, this camera uses superconducting detectors. This lets us measure the energy and arrival time of every photon without any false counts. You can think of it like a noiseless 10-color movie camera that works from the optical to the near infrared and is super fast. One downside is that it has to run at 90 millikelvin, but we know how to do that. We called this camera MEC, the M-Kid exoplanet camera. MEC doesn't work alone. The journey of discovery starts with the Subaru 8-meter telescope on Mauna Kea, the crown jewel of the National Astronomical Observatory of Japan. This giant telescope and the amazingly clear and stable skies of Mauna Kea give us pretty much the best starting point in the world to hunt for planets. Once Subaru is pointed at a target star, the light is focused on an adaptive optics, or AO system. The AO system corrects for the aberrations introduced by atmospheric turbulence. Think of these aberrations like the distortions you see when looking over the hood of a hot car on a sunny day. Since we know the star is a point source, we can measure what horrors the atmosphere has accomplished on the light with something called a wavefront sensor, and then try to reverse the damage with a deformable mirror, or DM. On Subaru, this deformable mirror consists of 3,000 linear actuators behind a flexible glass membrane. Did I mention we need to do this correction 2,000 times per second? Yeah, this is hard, and honestly, the performance of the AO system is one of the main things holding us back. After the AO system comes SkexAO, which does some more DM magic and also contains a coronagraph. A coronagraph is an optical system that blocks light from the on-axis primary star, but passes the light from planets that are as close as can be distinguished. This is called the diffraction limit. Finally, after this comes MEC. MEC images the light that comes out of the coronagraph in SkexAO. Other cameras can do this job, but what makes MEC special is that it has no noise and counts photons fast. Our eventual goal is to use this fast imaging to help the AO system clean up the image in a technique called focal plane wavefront sensing. We think this is critical for detecting planets smaller than the gas giants we can, with difficulty, image now. So that's MEC. Since we first deployed it in 2018, we have spent many nights observing with it. We've done some really cool stuff, like demonstrating how we can use the photon arrival time information to distinguish a companion from a background speckle, discovering a new companion around a nearby star that is probably a brown dwarf, and even doing some work imaging debris disks. However, as you might expect, MEC is super complex, and like most first product iterations, MEC has some rough spots. We are going to use this NSF funding to upgrade MEC into MEC Prime. There are 5 areas we're going to improve. First, we need to upgrade the MEC detector array. We don't need a bigger array, since all the planets are close to the parent star, but on MEC only 7 of the 10 readout lines worked, so our field of view wasn't as big as it was supposed to be. We are working with Lincoln Labs and their amazing superconducting device foundry to make some awesome new arrays. We already have some very promising results. We're also going to put an anti-reflection coating on this array, which should increase our quantum efficiency to at least 80%. Second, MEC uses some nice amplifiers called high electron mobility transistor amplifiers, or HEMTs. These amplifiers have a noise temperature of 4 Kelvin, which is so 2015. We are going to upgrade MEC to use radical new quantum-limited traveling wave parametric amplifiers, or TUPAs, with an effective noise temperature of a couple hundred millikelvin. This, combined with the new array, increases our ability to distinguish colors from about 5 colors to at least 20. This will have a massive science impact. Third, we're going to completely redo our room temperature electronics readout. We're going to use the Gen 3 readout system Jenny recently talked about in her thesis defense, so click on the card above to learn more about the readout. Fourth, we're going to improve the 4 optics and IR filters. These are some quality of life improvements that were annoying to work around, but in the end didn't hurt performance that much. Fifth, we're going to optimize for remote operations. When we designed MEC, we had no idea a global pandemic was incoming, and we expected to actually be at the summit to use it a lot more frequently than we actually were. We're going to build it so that we can do everything possible without needing someone to flip a switch at the summit, which I'm sure the Skexeo crew, who has been graciously supporting us, will appreciate. Once all this hardware work is done, our 2 graduate students on the project will work hard to develop the algorithms and control software to make focal plane wavefront sensing actually work reliably on Sky. And then we should become the most sensitive planet imager in the world. Okay, back to it. Okay. Our goal is for Mech Prime to detect the first planet in reflected light. All current exoplanets that have been imaged are young, hot planets imaged in self-luminous infrared light. In order to see older and cooler planets like Earth analogs, we need to be able to see exoplanets in reflected light from the parent star. While Mech Prime on an 8-meter telescope won't be able to see Earth-like planets, it may just be able to see a system like GJ876b, a nearby gas giant orbiting close to a small red star in reflected light. This demonstration is key to getting funding to put a system like Skexeo and Mech on a 30-meter class telescope, where detecting and characterizing Earth-like planets around nearby red dwarf becomes a real possibility. As part of this NSF grant, we have funding to film this process and make these YouTube videos. So like and subscribe to follow us on this most excellent adventure. The next episode in this series should see us go to Hawaii and pack up Mech and ship it home to begin the upgrade.